So we already have a pretty good tool set for NP completeness. We have sat, we have vertex cover, we have independent set, we have click, and we have shortest tour, and I guess also traveling salesman. In some way it's amazing, isn't it, that all of those problems here are NP complete, which means in a way they're equally hard to solve, although they're all quite different. Now, I promised you a library of NP completeness, so what I am going to give you now is 4 additional NP complete problems that are often very, very useful for showing NP completeness or also for recognizing NP completeness, because even before you do a formal proof, it's usually a good idea to say, oh, this problem, this looks very close to SAT, we better be careful, this could be NP complete. So you don't always have to do the formal proof, it can also be a good indication of how hard a problem could be. The 4 additional problems I would like to show you are a problem called 3-SAT, a problem called K-coloring, a problem called packing, and a problem called common substring. So 3-SAT is basically SAT, but there's one restriction, and that is that each clause has exactly 3 variables. And that, of course, is a nice assumption to make in many proofs of NP completeness, because if you have exactly 3 variables in each clause, these proofs often become easier to read and much cleaner. As a side info, 2-SAT, so where each clause has just 2 variables, is solvable in polynomial time. So one number here can make a difference. And the resulting 3-SAT formulas look like this. So you have 3 variables here in this clause, then 3 variables here, and of course with another index, and so on. K-coloring asks you if you can color a graph with K colors. So K is given as part of the input. And what is meant by coloring is that you give each vertex a color, such as here. So we color this one red, this one green, and this one also green. The constraint is you cannot color 2 vertices with the same color if they are connected by an edge. So this here would not be allowed. And actually the graph I've drawn here cannot be colored with just 2 colors. So you need 3 colors to color this graph. This here, for example, would be one solution. It cannot be done with 2. And of course that is stated as a question. So is it possible to color the graph using K colors? For packing, you have given a number of containers and objects, and the containers have a capacity, and the objects have a value, and a capacity requirement. So you have containers like this. They can be of different size. And then you have objects. You have little objects, you have big objects, you have very big objects, and they all have a different value. So this might be not so valuable, this might be a little bit valuable, and this might be very valuable. So usually you cannot put all of these objects here into the containers. So the question is, what is the maximum value that you can put into the containers? And of course you could have the case that, for example, the bigger object is actually worth less than the smaller object. So there's lots of different combinations here. And we'll actually investigate this problem a little bit more in one of the next units. Now, common substring is actually a misleading name because some people use this in a wrong way. I've seen this happen before. It actually should be called common subsequence. If somebody says common substring, better ask them if they don't mean common subsequence, because common substring is actually not an NP complete problem. And common subsequence is the following problem. You're given 2 strings, so string 1 and string 2, say lemonade and blender. And what is the difference between a substring and a subsequence? A substring is always lots of characters that are one after the other. For a subsequence, you can basically skip certain characters. So E, N, A, E is a subsequence of lemonade, but not a substring. And actually, we'll do this as a little brief quiz. What is the longest common subsequence of lemonade and blender?